Hey everyone, we left off last time with the first isomorphism theorem, and now we're going to move on to a new chapter. Our goal is to understand quotient groups, and one of the main tools that we're going to use to understand quotient groups will be the first isomorphism theorem. And so, but this is a new chapter, so chapter 15, quotient group, what's it called? Computations. Now, so first I want to give you kind of a picture of what a quotient group feels like, what it looks like. So let's start off with a normal subgroup, and let me call it N. It's typical, now that we have this idea of normal subgroup, it's fairly common to refer to a generic normal subgroup using capital N instead of the standard H for subgroup. So let's start off with a normal subgroup of G. The mapping eta from G to G mod N, defined in, this is going to be the obvious way, so defined by eta of little g, right? So we're going to plug in a little g, and out comes the corresponding coset, g times n. This is called the natural projection. So this is the natural projection of G onto G mod N. So what does it do? It just associates to each element of G its corresponding coset, G times N. It's easy to see, so well, you can compute this if you like, so it is easy to see that eta is a homomorphism with kernel, so the kernel of eta is exactly equal to capital N. Now, if you like, I mean, we can say it this way. So this gives a converse. Let me just put it in quotes here. I don't really care about the fact that it's a converse, but a converse to, and this was lemma 14.2. So lemma 14.2 said that the kernel is always a normal subgroup. This goes in the reverse direction, right? We started with an arbitrary normal subgroup and showed that it is the kernel of a homomorphism. So what we have here is every normal subgroup is the kernel of a homomorphism. I mean, it's not really that exciting, this converse, so to speak. But now what we have is kernels are always normal, and normal subgroups are always kernels. So, it just comes right from this computation here. Now, here's what I want to do though, is I want to use this mapping to get kind of a picture of what a quotient looks like. All right, and I want to leave this portion up here. So I'm going to draw G as a square, right? So this G, this square right here represents G. Where do I want N to be? Oh, yeah, that's fine. I wish I would have drawn this a little nicer. Draw a better square. It doesn't have to be a perfect square either. Okay, so here's capital G. And then you can think of this vertical line segment right here, you can think of that as N, if you like. And what I want to do is imagine that N, remember the set of cosets is a partition, and so N, or the set of cosets, chops our group G up into a bunch of non-overlapping pieces, right? So each time if I take a little G, and let's say little G is right here, then think of this strip right here. That is the coset Gn, right? So n, in fact, I guess I should put it right here like that. So there's n, right? The identity, you could say, is sitting right there. So the identity E times n. And each time, if I choose an element, so let's say little h, then the corresponding vertical strip, right, that one right there, is little h times n. If you multiply g times h, maybe g times h, this is just a schematic here, but there's g times h, and then the corresponding strip right there is gh times n. Now, remember that the quotient G mod n is the set of all left cosets. And so for each strip, right, sitting inside capital G, there's a corresponding element in G mod H, right? So for example, right, this right here, this dot right there would be capital N. This one would be little g times n. This one right here would be little h times n. And then that one right there would be gh times n. And you can view this as all happening under the map eta that maps from G to G mod n. So one way to think of how a quotient, what a quotient is, the action that that the quotienting process is, it takes the group G and smashes it down so that for every left coset, there's exactly one element. Remember, the elements become, or the elements are, the cosets. All right, so here's a picture of how the quotient behaves, if you like. Now, remember this example that we did? Let me just kind of remind you. So, well, in fact, I'll remind you by using the first isomorphism theorem to do it. So, let's define phi from, R to C star by phi of, I'll use, I guess I'll use little x. So phi of x equals e to the 2 pi I x. So then, and you can check, so then phi is a homomorphism with the kernel of phi. So let's see now, who would the kernel be? It will be the set of all things that go to the identity in C star. The identity is 1. To get this equal to 1, I need x to be an integer, and so the kernel of phi is equal to z, and the image of phi, well, it's the set of all things in the form e to the 2 pi I x, where x is a real number, that is equal to the unit circle. So now, by the first isomorphism theorem, R mod z, which is equal to R mod the kernel of phi, is isomorphic to the image of phi, which is equal to u. So here's a nice quick proof, right, that R mod z is isomorphic to the unit circle. That's an example we did a little while ago, maybe 1 or 2 lectures ago, right? As an example of understanding the quotient group or understanding a quotient. And I had to kind of draw a picture of stacks and so on and say, oh, well, let's think about this. It seems reasonable that this would look like a circle. Here's a straightforward direct proof, a straightforward application of the first isomorphism theorem that tells us immediately that R mod Z is isomorphic to the unit circle. Right? So that's a typical way, and we'll see lots of examples of this, but this is a typical way, and I guess this is maybe our first real example, typical way of applying the first isomorphism theorem. Right? You have a homomorphism, right, onto your targeted group, the thing that you think your quotient is isomorphic to, and you concoct that homomorphism to ensure that the kernel is exactly what you need it to be. Right? So this was a first example. We'll see lots of examples of doing this. Now, not everything that we do involving kernels uses the first isomorphism theorem, but it is a very powerful tool for understanding quotients. Now, our first result, so this theorem, or I mean this chapter, it's called Quotient Group Computations, I think, or is it Computations? Yeah, and so we want to be able to understand what a quotient group is. We'd like to be able to say, oh, I understand this particular quotient. I understand its behavior. And one of the key things that you might want to ask yourself is, if you have some group and a normal subgroup and you take the quotient, to what extent do the properties in the quotient mimic the properties of G, right? How many of those properties are shared between the two? So our first theorem, let's let N be a normal subgroup of G. Two pieces or two parts to this. Part A, if G is abelian, then G mod N is abelian. And part B, if G is cyclic, then G mod N is cyclic. So a quotient of an abelian group is abelian, a quotient of a cyclic group is cyclic, right? So here's two situations where the properties of G are shared by the corresponding quotient. And the proof in both cases is pretty straightforward, but let's work through. Right. So for part A, if A and B are in G, then let's see, I want to show that G mod N is abelian, so I will need to show that the elements can be multiplied in either order. The elements are AN times BN. That's a typical element. That's equal to AB times N, which is equal to BA times N, because capital G is abelian, I can reverse the order of A and B. And then this is equal to Bn times An. And so that does it, right? So therefore, G mod N is abelian, right? You can multiply in either order and you get the same thing. For part B, so now we want to assume that G is cyclic and we want to show that G mod N is cyclic, so we need to construct a generator for G mod N. So for part B, let's let little g in capital G be a generator, be such that the subgroup generated by G is equal to capital G. Then what? Okay, so we need a generator for G mod N, and I mean, I think the obvious choice is going to be, what do you think? I'll give you a second to think about that. So we've got our generator little g, who's going to generate all the elements of G mod N. So then if x, let's say xn. How do I want to say this? Yeah, let me make a better sentence. So let's choose x times n in G mod n. Letting little n in Z be such that, now what do we know? X is an element of capital G, and because little g is a generator, we know that x is equal to g to the n for some n. So be such that x is equal to g raised to the n. Then we have x times capital N is equal to g to the n times capital N, which is equal to gn raised to the little n. So what have we shown now? We've shown that every element in the quotient can be expressed as a power of this particular element of the quotient. Therefore, G mod n is equal to the subgroup generated by Gn, which tells us that it's cyclic. Right? We produced a generator. Let's see, so now I'll do a couple examples here. So first example, I'd like to, so I'm going to say it this way, identify Z8 mod the subgroup generated by 4. Right, so 4 is an element of Z8. We can look at the subgroup generated by 4, and this is going to give us some element, some group, some quotient group. So let's see, who do you think it's going to be? Well, one thing we know from our previous theorem is that since Z8 is cyclic, so is Z8 mod ideal generated by 4. So since Z8 is cyclic, so is Z8 mod subgroup generated by 4. So what we have then is a cyclic group right here. If we knew its order, we could say exactly who it's isomorphic to. And by the way, when I say identify, what I want to do is produce a familiar group to whom this thing is isomorphic to. That doesn't sound right, but you know what I mean. Okay, so now I'm going to start the next sentence with since also. Since the order of Z8 mod subgroup generated by 4 is equal to 8 over 2, which equals 4, we conclude that Z8 mod subgroup generated by 4 is isomorphic to Z4. Another example. Okay. So this is going to be another identify type problem. So in Z, I can read my writing here. Z6, I think that's the Z. Yeah, Z6 cross Z8. So in Z6 cross Z8, let H be the following subgroup, and it's going to be the subgroup generated by 2 comma 4. And so if we write this out, let me write it out right here. So it's going to have 0, 0, and 2, 4. And if I add it to itself, that will be 4 comma 0. Add it to itself again, it will be 0 comma 4. Add it to itself again, I'm going to get 2 comma 2 comma 8. Wait, add it to itself, that'll be 2 comma 8, which is 2 comma 0. Add it to itself again, that will be 4 comma 4. And then add it to itself again, I will get I'll get 6 comma 8, so that's the identity. And so what do we have? 1, 2, 3, 4, 5, 6. Yeah, we have a subgroup of order 6. Now, since the order of Z6 cross Z8 is equal to 48, we know. Oh, and by the way, Z6 cross Z8 is an abelian group, so this quotient, so H is a normal subgroup, which was, we can talk about the quotient group. So we know Z6 cross Z8 mod 8 has order 48 divided by 6, which is 8. Okay, so now, right, since Z6 cross Z8 is abelian, right, by our previous theorem now we know that any quotient of an abelian group is abelian. So since this is abelian, we know that Z6 cross Z8 is abelian of order 8. So what that means then, if we want to figure out exactly who this quotient is equal to, or isomorphic to, we have 3 choices. Whoops, I'm sorry. I missed my quotienting thing right there. Sorry, hopefully you all noticed that I made a typo there. So this quotient is abelian of order 8. So thus, the quotient Z6 cross Z8 mod H is isomorphic to 1 of the following. Right, so who are our possibilities? Z8, Z2 cross Z4, or Z2 cross Z2 cross Z2, according to the fundamental theorem of finite abelian groups. Right, that's our list of abelian groups of order 8. Okay, now, so I need to figure out, what I want to do is figure out who is this quotient isomorphic to. It's isomorphic to one of those 3 right there. And so one way to go about this would be to actually write down who the cosets are, right? There's going to be 8 cosets in here, so you could just sort of brute force it, write out the cosets, and then compute orders of those cosets. And so, for example, if you get an element of order 8, then you know that you're looking at Z8, or it's isomorphic to Z8. Right? If you have only elements of order 1 or 2, then you know that it's isomorphic to this one. If it's somewhere in between, then it'll be the one in the middle. So let's just say one option would be to compute orders of cosets. But that's going to be kind of tedious to write out the cosets and then compute orders. That'll just be kind of a pain. Instead, here's what I want to do. So instead, what I'd like to do is apply the fundamental theorem, the first isomorphism theorem. And so let's define phi from Z6 cross Z8 to Z2 cross Z4 by phi of AB is equal to the ordered pair A mod 2 and B mod 4. Now what you can do is if you check, so I'm just going to say check that phi is an epimorphism Remember, epimorphism means onto homomorphism with the kernel of phi equal to capital H. In this case now, if we apply, and I mean, let's just like quickly, remember what H was. It was the subgroup generated by 2, 4, right? Well, clearly, if I put 2, 4 here, I'm going to get 0, 0, right? And so every power of that element is also going to be in the kernel, right? So the kernel of phi is equal to H. So then you can apply the first isomorphism theorem. So by the first isomorphism theorem, Z6 cross Z8 mod the kernel, which we know is H, is isomorphic to the image because it's onto its image is Z2 cross Z4. This is how you use the first isomorphism theorem. And I trust me, we'll see more examples. This might seem a little bit weird. Well, how did you know to come up with that? Well, this is a fairly reasonable homomorphism to cook up, right? Reduce the first mod 2, reduce the second one mod 4, right? And you get some element in Z2 cross Z4. Then you just figure out who the kernel is. Right? So, anyways, that's kind of the flavor of how a first isomorphism theorem type proof or type application comes up. Let's do one more. Let me see what time it is here. Yeah, we've got time for one more example. So, and this is going to sort of reprove something. So recall that the determinant, which goes from GL, and do I just want to do N? Yeah, GLNR to R star is a homomorphism where, let's see now, who would the kernel be? Well, let's see, the identity in R star is the number 1. And so the kernel of the determinant is going to be the set of all matrices whose determinant is equal to 1. And so where the kernel of the determinant is equal to the set of all matrices whose determinant is 1. Now, since determinant is onto, that should be fairly obvious. Take any number here. I bet you could come up with an invertible n by n matrix whose determinant is equal to that particular number. So since the determinant is onto, we have that GLNR mod the kernel, which is SLNR, is isomorphic to the group, the multiplicative group of non-zero real numbers. So that's pretty fun. This is really fun. Not just pretty fun. This is fun. I I think I'll leave it here for now, and we'll pick up with this idea in the next lecture.